problem 4 talks about myoglobin and hemoglobin and how they are oxygen-carrying molecules in the human body. And then it gives us formulas for how myoglobin and oxygen saturation relate to pressure. So M of P, you get myoglobin as a function of pressure. And then H of P, which is hemoglobin as a function of pressure, with M of P being P over 1 plus P, and HP being P to the 2.8 over 26 to the 2.8 plus P to the 2.8. And now it asks us to give the graphs of these guys on the domain 0 to 100 for P. And then which is which. So, it gives us these graphs, these two. So what I did for this, and it's actually going to help us out with the rest of the problem, is I brought out my calculator, and you'll see I just went to the y equals function. This is a TI-84, and then for y1 put in the formula for M of P. Eventually I did all three, or I did M of P, H of P, and then I did y1 minus y2, which is just M of P minus H of P. Then put that in, and then I adjusted my window so that my x-min was -1 because I wanted to be able to see some of the origin, and then my x-max at 120 just because our domain is between 0 and 100, and P is, I'm using x instead of P, but it's going to be on the x-axis, so I put a little bit higher so that I can see it. I put my y-min to -0.1 and my y-max to 1.1 since we're using a domain of, or a range of 0 to 1. This is because this is in percentages, and it's going to be 0 to 100% basically. But again, I went just slightly outside of 100% so I could see the origin, and then made the scale at 0.2 with a resolution of 1, and then delta x being 0.4 something, so not as important. But then what is important is that you go to table set here, and this is for later on, and I changed my intervals into 20 because 1, that's kind of what the tick marks that were given at the bottom are, and then 2, because later on in the question it asks us to find H of P and P of P at values like 20, 60, and 40, 100, etc. So come over to the calculator, press y equals, plug in our formulas, and you press graph, and you can see here's our three graphs. So blue is going to be, let's see, y1, so y1 I believe was M of P, yeah, M of P, and then red, which is going to be H of P, you see that there, and then M of P minus H of P for green, which we'll get to eventually. But you can see that if we compare it to the graph we're given here, it's very easy to tell which one was which, and basically what we got is that M of P is increasing way faster, while H of P kind of takes a pressure of like 60-ish to start really catching up. Anyway, so the next question asks, if pressure in the lungs is 100 torrs, that's the unit that we're using for pressure, what is the level of oxygen saturation of the hemoglobin in the lungs? And so what we can do is we can either plug in 100 for our HFP formula, or what we can do is, since we already have it punched into our calculator here, we go to our table function, so just press second and graph, and that'll get you to the table function, and it'll spit out a bunch of values. So when x, or in this case P, equals 100, H of P is going to equal 0.9901, or 99.01%. And then this is the basis for how we're going to figure out pretty much everything. So I just wrote down the important numbers in the table here. Understand that these are just percentages of oxygen saturation for hemoglobin and myoglobin. So there you go, M of 20, 95.24%. Oh, that's the next question. Okay, next question. The pressure in an active muscle is 20 torrs. What is the level of oxygen saturation of myoglobin in an active muscle? Meaning, what's the oxygen saturation when P is 20? what is the level of hemoglobin in an active muscle. So again, our table makes it really easy. When X is 20, we have 95.24% and 32.42%. You can see that on our table here. And it makes sense if you look at our graph. It takes a little while for the hemoglobin to catch up. And then we have D. So define the efficiency of oxygen transport at a given pressure to be MFP minus HFP. What do you know? We have that already written there. Y1 minus Y2. In case you're wondering how to do that, what you do is you end up pressing alpha graph, I believe. Oh, wrong one. Oops. Alpha graph. Nope. Alpha trace. There we go. And you can just press enter for these guys and it'll put in place your Y1 and Y2 for that. So Y1 is MFP, Y2 is HFP, so Y1 minus Y2 is MFP minus HFP, which is exactly our definition. Then ask what the oxygen transport efficiency is at 20, 40, and 60 torrs, and then sketch the graph. And so again, we just go over here to our table, press second graph, get to table, and we have Y3 in green. 20, 40, 60, 80. We just copy those down, put them down, and just notice that we're basically getting less efficient as pressure goes up. And you can see that as well visually in the graph. So it's highly efficient up front, and then not so much later on. And then it asks other conditions under which transport efficiency is maximized. So if we look at the graph here, we can see that it's maximized. The short answer is yes, somewhere around here. But how do we figure out what that maximum is? Well, we just come over here. We want to calculate something, so we go second trace, which gets us to the calculate function. We want to find the maximum, the local maximum. So we press enter, and then come left a little bit of the maximum, press enter, and then it's gonna ask us to come right. We're just oh no, look what I've done. Okay. What you also need to do is make sure that you are finding the maximum for the right line. So we want it to be the maximum for our green line. So now that we're on the green line, we can go to the right and left. Sorry, this is a little bit lengthy, but I think this is going to be a good video. And then to the right, press enter. And it's going to ask us to guess. Not super important, I always just kind of go somewhere in the middle. Press enter again, and what you get is a value that spits out right at the top. The maximum is 8.0666, and Y is 0.8533 or 85%. So that's going to be maximum efficiency when the pressure is 8.0667 torrs.